Thank you. So let us define convergence. So if at a certain time you have a flow that is established from a source to a destination, and at time t1 you have a failure, the connectivity is lost. At time t2, routing is established again, an end-to-end alternate path to reach the source to destination. We define T2 minus T1 as the loss of connectivity or the convergence we are going to focus on during this presentation. And in the previous NANOC we focused on IGP. Here it's with convergence related to BGP reaction. So the BGP Prefix-Independent Convergence feature, which we call BGP PIC, has two flavors, the core flavor and the edge flavor. So let us first define the core flavor. In the core flavor, we would look at a core link or a core node failure. So for example, PE1 in this drawing has installed 350,000 BGP routes with BGP next hop being PE2. In the representation of the routing table of PE1, we see these 350,000 routes as green routes. PE1 has an IGP path to reach PE2. It is represented as the yellow entry in the routing or forwarding table. We say that the BGP routes depend on the IGP route. The question we analyzed in BGP PIC Core is, if there is a failure within your AS, which triggers an IGP convergence, and we know from the maturity of the technology that the IGP convergence will take a few hundreds of milliseconds. So in a few hundreds of milliseconds, PE1 will update the yellow entry with a new IGP path here, post2. The question we are now looking at is not related to IGP convergence. It's related to how quickly will the green entries, the BGP destination, leverage the new IGP path to the BGP next hop. And the requirement from you is immediately. BGP PIC Core guarantees that it occurs immediately. We first prove it, and then we will explain how it is achieved from a technical viewpoint. So this is the measurements related to the case study we just described. The unit under test is a CRS running IOX 3.5 in an ISIS topology of the complexity of a tier 1 service provider. We have 5,000 ISIS prefixes in this topology, and one of them is the BGP next hop that installed so many BGP routes. Obviously, it is important, so in this case study, we placed it in the critical list, which makes sure that it will be among the first 500 to be updated upon IGP convergence. It's the typical IGP convergence chart. So on the x-axis, you find the IGP position. On the y-axis, you see the convergence or loss of connectivity measured with real packets sent to this destination, and the unit is in milliseconds. You see multiple curves because this testing is reproduced 100 times, and we plot the minimum, the median, the percentile 90, and the percentile 100, or the maximum. Again, the interest is the BGP behavior, or how BGP destination leverage this. So we focus our attention to the right of the chart. And there we see 4 points. The first one is the BGP next hop. Without any surprise, it converges extremely quickly because it leveraged IGP convergence. We see in this test, sub 100 milliseconds, it is not surprising. That's the level of technology achieved today. But the interest is the 3 other points. The 3 other points are respectively the first, the middle, and the last BGP prefix that depend or recurs on it. And there are 350,000 of them. And you see that consistently through measurements, these destinations leverage the IGP convergence of the BGP next hop. It's an immediate leverage of the IGP convergence. This is significant. How is it achieved? That's the interest of this presentation, to explain how it is achieved. It is achieved through a hierarchical organization of the forwarding table in the data plane. In this representation, you see on the left the BGP prefix, the 350,000 BGP prefix are installed as FIB leaves on the left of my diagram. These 350,000 BGP prefixes, they have the common reachability from a BGP viewpoint. It's the same BGP next hop. The BGP LDI is a memory entry in our organization, which in our FIB organization, which represents this BGP connectivity. It could be multiple BGP next hop if it was multipath, or it would be one single BGP next hop, which is this example. From the BGP LDI, we have one pointer that goes to an IGP LDI. The IGP LDI represents the connectivity in the IGP to go to that BGP next hop. Again, if there would be multiple ECMP IGP paths, you would see multiple pointers leaving the IGP LDI box. Here, there was one single path, so we see only one single pointer. It is obvious, as soon as you have this hierarchical organization, that as soon as you have the IGP convergence of the BGP next hop, which means that you have a modification, an atomic modification of the IGP LDI to use a new outgoing interface, that all the BGP dependents leverage from it immediately. It's extremely also scalable and robust from an implementation viewpoint and a utilization of the control plane resources. In the past, most, if not all, router architectures were built with flattened FIB, which means that when, obviously, the control plane always managed the information in this hierarchical manner, but when it's about to write it into hardware, flattening is done. It means that each FIB leaf is immediately connected to its immediate outgoing interface. The flattening advantage is that the lookup is easier, so you either have higher PPS or you have simpler hardware to achieve a given PPS. The drawback it has is conversion speed, because obviously if the IGP connectivity change and you need to change the OIF used by the IGP LDI in a flattened organization, the line card CPUs now to go and rewrite all the dependent BGP entries in a linear process. And you can imagine that if you have hundreds of thousands of BGP dependents, this extra workload is going to represent multiple seconds. And so the IGP convergence, which is sub 200, a few hundreds of milliseconds, is by far not the one you would see for BGP destined traffic, which is really what you care about. So, hierarchical FIB organization in the data plane for the forwarding table has the following advantage. The BGP PIC Core feature, which is that the BGP dependents leverage the IGP convergence of the next hop immediately. But it has also scaling and robustness advantages. To understand the robustness gain, think about a link flap in your own AS. From an IGP convergence viewpoint, who cares? It's extremely quick. There is no, it doesn't going to waste your resources. It's a few hundreds of milliseconds. We download the few IGP prefixes to the line card and that's it. If the link comes back up a few hundreds of milliseconds later, it's the same process and that's it. But if you bundle this with a flattened data plane architecture, then it means that at the down transitions, you trigger on the line card multiple seconds if you have hundreds of thousands of dependents of line card CPU utilization at 100% to just recopy everything. And so the transition back up is delayed by these few seconds. And so in total, you also have line card CPU that is driven to 100% just for no good reason in this case. So let us now focus on PIC Edge. PIC Edge is a data plane protection mechanism which is triggered by IGP convergence upon border router failure or peering link failure in order to immediately protect BGP destined traffic via alternate, still viable BGP next hops. It doesn't require any configuration, any tuning, any design. It doesn't require any tunnel of what swarms to operate. It's just automatically done by the software. So we're going to explain this topic in multiple stages. First, I'm going to use a very simplified case study. I'm going to report measurements on it to prove it works. And then most important, what is the interest, is to explain how the data plane achieves this, how we build the forwarding table to achieve this behavior. And then we will finish with a bit more details on what is behind this technology. So this case study, two ISPs, the gray one and the yellow one, peer at multiple locations. The yellow ISP advertised 350,000 BGP destination to the gray ISP. Router R1 and router R2 set next hop self. rather R3 as IBGP sessions with R1 and R2. R3 is configured for multipath. R3 is going to install these 350,000 BGP destinations as multipath entries with two next hop, R1 and R2. We're going to send traffic from the left of R3 to these destinations in the yellow ISPs, and we're going to fail router R1. And we are going to measure how long it takes for the traffic to be recovered through the remaining peering link between the two ISPs. The unit under test is a 12K running IOX 3.3. The result is sub 180 milliseconds. It is totally expected because it's the IGP convergence time to conclude with the deletion of the border router. So let us look again at this case study. In a few hundreds of milliseconds, upon border router failure, it is clear that R3 will conclude with this simple fact: I delete the next hop of R1. So this deletion of the next hop triggers the data plane pre-computed protection mechanism, which is going to push at that time in a prefix-independent manner all the 350,000 BGP destinations via the remaining peering link, without any configuration, without any policy constraint. In this simplified example, the same 350,000 BGP routes are advertised on the two peering links, but you do not need this. Looking at this chart, one question that could arise is, why is it that some of the flows that were used to measure the convergence report zero loss of connectivity? That's normal. Before the failures, some of the flows used for the measurements go via the top peering link, some go via the bottom peering link. You have load balancing on a per flow basis. So obviously the flows that were routed via the bottom peering link are not impacted by the failure, and so they report zero loss in this case. So again, the key thing, and I insisted upon it, is that it is a data plane protection mechanism triggered by IGP convergence. Yes, the term is BGP because the one that gains this service is BGP destination, but BGP is not at all involved with this. This is purely a forwarding table organization trick coupled with IGP convergence. So when this happens, this exact case study with a witness, a measured loss of connectivity of sub 200 milliseconds, if you do the same analysis, but now at the control plane level, which is not what the user would see, the customers would perceive, but at the control plane level, BGP will take like several tenths of seconds to converge. And so if you do the same testing without this data plane protection mechanism, the experience of the customer is multiple tenths of seconds of disconnectivity. And so the impact of this technology is huge in terms of service experienced by customers. Now, again, what is interesting is what is the building block behind all this. This is the hierarchical organization of the forwarding table in the data plane again. So the 350,000 BGP destinations are inserted in the forwarding table as FIB leaves. They are all sharing the same BGP connectivity. It's a multipath set of two next hop, R1 and R2. This is represented automatically through FIB intelligence. It understands this sharing principle. And so they are all going to have pointer indirection to the same memory entry, which is the BGP LDI, which has two pointer indirection to go to the IGP LDI, the representation of the IGP connectivity of the two next hops. And so it's obvious, as soon as you see the drawing, that you would think, why was it not like this before, that upon IGP convergence, it ends up with the deletion of the top IGP LDI. And the only thing that is required is to, at deletion of the IGP LDI, to check if they are dependent or children BGP LDI, and in place modify them to only use the remaining valid next hop. It's obvious and simple. So now that we have seen how it works, what is the service experience or the gain in service experience by the customer, let us now bring a bit more details to this. There are multiple assumptions that I made for BGP PIC Edge to work. and we're going to walk through them. The first assumption is that the trigger must be an IGP-based deletion of the BGP next hop. It is granted for border router failure. It is granted for peering link failure if the border router does not run next hop self. If the border router does run next hop self, then the solution is simply BGP PIC-Edge primary backup. What is BGP PIC-Edge primary backup? Next assumption. The second assumption I made is that R3 installs these 350,000 BGP destinations as multipath BGP routes. And you understand, in my example, why I need this multipath entry, because when my top IGP LDI is deleted, yes, I could think of in place modifying the BGP LDI, but it will only be useful if I have another path, hence my multipath assumption. It is clear that you can extend this to primary backup policy. You simply ask BGP to compute the BGP next hop as you have today, plus a backup next hop. And then we use the same organization to achieve it. It will be provided in the future as a software enhancement. The third assumption, which is that the communication from R3 to R1 or R2 is over border router to border router encapsulation. It just makes sense. This is the initial way that IGP BGP routing was designed. It was not done 15 years ago because at that time NCAPS DCAPS was difficult. Mature modern routers support NCAPS DCAPS at line rate over MPLS LSPs, over IP push and pop header. I assume it, but I don't see it as a constraint at all. It's beneficial in this design study, but we can list many other advantages to run an IP network over IP NCAPS or MPLS NCAPS, border router to border router. The fourth assumption I made is that R3 is connected to R1 and R2 via IBGP sessions. It's obvious. For this to work, I need two paths before the failure, either to do multipath or to do primary backup. In the VPN world, because people typically design with unique RD allocation, I don't have any problem for this assumption, because even if I use route reflectors, they will not hide any path, and any border router will receive all the paths that exist, and it will be possible. But in the internet case, it is difficult, and most likely impossible to deploy actually if route reflectors are used, because the route reflector is designed to leak one single path to its clients. So although everything could be done to have this backup or multipath recovery, if you have only one path, you cannot trigger the mechanism. So how, if you're interested in this, how are you going to use it for internet? There are short-term, long-term solutions to this. The short-term solution is to add IBGP sessions to other route reflectors or other border routers to get the additional path. Not sexy, but potentially one option. The other options is to run internet in a VERV or internet as a VPN. Then again, you fall back on the RD uniqueness, you bypass the route reflector hiding, and that's available. The long-term solution for this is obvious. This is the add path capability that is currently defined at the IETF. So this assumption is not obvious. I recognize it in the IPv4 internet case. I listed a few short-term solutions. The long-term solution likely will be add path. In the VPN world, which was really our motivation for developing this technology, especially to deal with border router failures, which are catastrophic. You cannot imagine to deal with a border router failure from a BGP control plane convergence viewpoint that's multiple tens of seconds. So in the VPN world, there's no issue. That assumption is granted. So we reached the conclusion. The real message or the real technology topic that is behind this presentation is not BGP. It is about how to architect the data plane forwarding table. And that should have been the name of the presentation, but then it's a bit less sexy, less related to perceived service, so we call it BGP Prefix-Independent Convergence. But the real technology behind it is hierarchical FIB organization of the data plane. There are three advantages to this: scaling and robustness, and convergence. specifically BGP PIC Core and BGP PIC Edge. BGP PIC Core guarantees that upon core link or node failures within your AS, BGP destinations will leverage the IGP convergence of the BGP next hop immediately, thanks to the hierarchical organization. BGP PIC Edge is a data plane protection mechanism which, upon border router or peering link failure, thanks to IGP convergence, trigger a protection of the BGP destined traffic via alternate, still available BGP next hop. Many thanks for your attention. If you have any questions, they are welcome.
Himanshu from Alcatel. You said you do this for VPNs as well?
Yes.
So do you track the IGP next hop or the LSP endpoint? I mean, in IGP or the LSP database?
In this example, it's obviously the BGP next hop, so it's R1.
Right, but is it the LS? I mean, do you check whether the LSP label is available or not? Or
we can discuss it, but it's unrelated because IGP convergence is going to be triggered as a deletion of the next hop, whether you have an LSP to it or not. It's unrelated.
Okay, and just a side note, I mean, the whole technology is available in other vendors for several years, actually.
I would be surprised, but...
Okay. Well, if we have no more questions.